Okay, so now what we're going to look at is the application problems with these exponential functions. And so we're going to start with the compound interest, and we're going to start with kind of a simple one where it's going to basically get compounded yearly. So right here, it's compound interest is interest computed on the original investment as well as the new accumulated wealth. And so right here, if no time goes by and you take out a loan and you just hand it right back, then you're not going to really owe any interest. But if you want to take out a loan and say you're going to pay back 10% a year later, well, you're going to pay back your loan, which is P. P is known as your principal. And so that's going to be how much you borrow, and then plus the rate that they're going to charge you. Now, the way that that's going to work, we're going to put that, sometimes we like to use percentages, but whenever we're using a formula to compute, we're going to have to convert that to decimal format, and we'll go over that in just a second. So looking at the example that I kind of brought up, so if you were, let's just say you were to borrow, so A is going to be the accumulated value after each compounding. So for example, the principal, let's say you're going to borrow $100 and you're going to pay it back in 1 year, plus you have to pay 10% interest. So for 10%, you don't want to plug in 10 because that means you're going to pay back 10 times as much, right? And so what you want to do is you move that two decimal places to the left whenever you have a percent. So it'd be 0.10. And so when it comes time for you to pay your loan a year later, you're going to pay $100 plus 10% or point 0.1, which would be $10. So you're going to pay back the 100 plus $10. And so now you owe $110 for that loan. But let's say you say, you know what, I'm not ready to pay it back. Can you give me another year? Okay, sure. But you're going to be paying interest on that new $10, right? So not just the 100, but now plus that $10. And so that's where this formula comes in right here, where you just keep multiplying by 1 plus the interest rate right there. And if you were to continue that, basically the years that go by is going to be your exponent right there. So after t years, you're going to pay your principal back, plus r, and then raised to the power of t right there. And so that's the formula we're going to use on these first couple right here. And then, so the one that's listed here is actually known as a growth formula because it's going to grow higher and higher. And then we also have a decay formula where you would use subtraction instead, and that would be maybe if something were depreciating in value. And we'll look at an example of that too in a moment. So let's go ahead and look at our first problem here. And so once again, those variables are defined right here. Accumulated value, or sometimes we'll just say final amount. P is your principal or your initial amount, and then rate, and then time in years. So right here it says the fox population in a certain region has an annual growth of a rate of 9% per year. So 9% per year. It is estimated that the population in the year 2000 was 24,100. So the first thing they're going to ask us to do is come up with a model, a function to model this. So find a function that models the population um, t years after the year 2000. Okay, so this is gonna be a growth formula because they're growing, right? The growth rate. And so we're gonna be using this formula right here. So it's gonna be A equals, and so the initial principal, the initial population, we're gonna start in the year 2000. It's gonna be 24,100, so 24,100 times parentheses 1 plus my rate, which it's 9%, but you don't want to plug in a 9 because that'd mean that the population's going to be 9 times bigger each year. So we don't want to do that. We're going to move it two decimal places to the left. And so that's going to be 0.09. And then for now, we're just going to plug in t because they just want us to come up with the model. They didn't ask a specific year. Okay. And so T is going to be represent years from the year 2000 on. So what you're going to notice is in this part B right here, it says use the function from part A to estimate the fox population in the year 2008. So you don't want to plug in 2008. because we're looking, this formula is good starting in the year 2000. So for t, we're actually only going to need to plug in 8 for that. So we're going to go ahead, we're going to let t equal 8. So we're going to have a equals 24,100 parentheses 1 plus 0.09 raised to the power of 8. And so if we wanted to, you don't have to do this because the calculator is going to do a lot of this work for us. But if you wanted to go ahead and add that together, you could. So a equals 24,100 times this would be just 1.09 raised to the power of 8 like that. Now, depending on what kind of calculator you're going to use, you can either type this whole thing in at once, or you can kind of do it in pieces. Um, on the homework and exam, you should be able to use a scientific calculator. If you have a graphing calculator, that's great. Those are pretty easy to work with, but if not, you shouldn't have too much trouble with this. Just practice on your homework so you make sure you know how you want to input this to make sure you get the right answer. So with the scientific calculator, what's kind of nice about, this is a graphing calculator, but even with the scientific, you should be able to pretty much just type this in verbatim. So 24,100, then I'm going to open a parentheses, 1.09, close the parentheses, and then some of the newer calculators, when you press this little arrow button or whatever, this little caret, it will actually give you a superscript, and if it does that, great. If not, it means the same thing right here. So I'm going to raise it to the power of 8, and I'm going to put that in parentheses. It actually does not matter in this particular example, but some of the later ones it can, and I'll talk about that when we get to those. So automatically, I'm just going to always put my power in parentheses just to make sure, just kind of get that habit formed. And so let's go ahead and press enter. And so it says round to the nearest integer. So I'm actually going to round this up to 48,021. 48,021. So let's go ahead and put that here. So 48,021 is going to be our rounded to the nearest integer. So the fox population in 2008. So it's going to almost double in that 8-year span. Okay, so we're about to do pretty much the same thing, but now we're going to look at one of the decay ones. And so the only difference is we're going to use subtraction instead of addition. So let's look at this one. I like this one. So a car is originally priced at $35,000. It loses 13.5% of its value each year. What is the value of the car in 3 years? Let's go ahead and round to the nearest penny. Okay, so this will be my principal. That's the original value. Let me just go ahead and write the formula real quick. A equals, it's going to be my principal, and then 1 minus the rate that it's losing per year, and then raised to the power of time. So that's going to be my principal right there, the initial value that I pay for the vehicle. This is going to be my R value, which I will need to move that 2 decimal places to the left when I plug it into my formula. And t is going to be 3 years right there. So let's go ahead and plug that in. So A equals, let's see, the car is worth $35,000 when I buy it. And then it's going to be 1 minus, now I have to put 0.135 there. And then raised to the power of time, which in this case is going to be 3. And so you could clean this up a little bit, but like I said, the calculator is going to do most of the work for us anyway. So if you just want to leave it that way, and we can just type it in exactly how that looks right there. So 35,000, and then parentheses 1 minus 0.135, and close that parentheses, and then I have to raise it to the power of 3. And if I just put 3, that's fine, but once again, I'm just going to try to kind of get us in the habit of putting that in parentheses for later on. And then I'll go ahead and press enter. And so let's see, that car is now worth $22,652.51. And so let me go ahead and get a picture of that. All right, so that was going to be a lot for me to remember, so I went ahead and put a little snippet in here. So $22,652.51. So that's a big difference. And so whenever you buy a car, it's going to lose value right away. So something to kind of think about. Okay, so I have a couple more for us to look at, but we're going to be using some different equations. So this first one was just kind of, this is known as like simple interest from year to year. It's a pretty simple formula. And so think about especially the growth formula, because that's really what we're going to focus on moving forward, because we're going to kind of talk about investments. So if you invest your money, you want to grow it, right? So we're going to kind of focus on the growth formula. So if you look at this formula, the formula on the next slide is going to be very similar, except we're going to introduce one new variable here, and it's going to be added to this original formula that you're looking at right here. Okay, so the formula on the previous page is designed for annual compounding, okay? But the more often you compound, the faster your investment will grow. The following formula allows for additional compounding within a year's time. We'll focus on the growth model, so we're just going to focus on growth here. And so the only difference here is that n value. So it's still p times 1 plus r, but then we're dividing by n, and then raised to the power of time, but time's going to get multiplied by n also. Well, what is n? Well, n is going to be the number of compounds within a year. And so r is going to be the rate, and t is still going to be time. So what's going to happen here, we're going to add those variables in there, and when we compute it, like the more often that you compound, what's happening is your earnings, the money that you're earning from the investment is becoming part of the investment. And so the more often you do that, the better off you're going to be. And so we're going to do one where we compound it monthly and one where we compound it quarterly, which would mean 4 times within a year. And the difference won't be that big, but if we talk about doing that over like a 30 or 40-year period, then it could be a substantial amount. But this particular example, it'll probably be a couple dollars, the difference. It won't be a huge difference. So let's go ahead and look at our example here. So it says if $4,200 is invested at a interest rate of 3.9% per year, find the value of the investment at the end of 5 years for the following compounding methods, round 2 decimal places. So let's go ahead and write down what we know. So we know my principal, that's going to be what I'm investing. I'm going to invest $4,200. And my rate of return is 3.9%. So my rate is 3.9%, or as a decimal, because we're going to have to do this as a decimal, it's going to be 0.039. That's the number you got to use when we plug it into our formula in a minute. And then T is going to be, we're looking at 5 years. So we're going to take this formula, we're going to plug in all those values here. So let's see, A equals 4,200, parentheses 1 plus, so my rate is 0.039 divided by n, compounding. So for example A, we're going to compound monthly, so there's 12 months in a year, so n is going to equal 12 in this particular example, so 12. And then raised to the power of n times t. So this is where that parentheses comes in. You're going to want to do 12 times 5. 12 times 5. N is 12 and T is for 5 years. And so you could clean this up a little bit like the 12 times 5 and do some other stuff, but I would just go ahead and put this in the calculator, and as long as you use those parentheses in the right places, you should be in pretty good shape. So let me grab my calculator. And here we go. So let's see, I have to start out with the 4,200 parentheses 1 plus, and then this fraction, I can just type it in as I see it. So it will be 0.039 divided by 12, close it, and then now we're going to raise it to the power of 12 times 5. So if I don't put the parentheses, it will not read this correctly. What it will do is it will raise it to the power of 12, and then once it gets that result, multiply it by 5. So I have to put the times 5 with it as part of the exponent in parentheses. If I don't do that, like I said, that times 5 will occur after the fact. And my answer would be kind of crazy. And so hopefully it'd be kind of obvious that something went wrong. So let me go ahead and press enter. And so the investment, that's pretty good. It grew by almost $1,000 in that time period. So that's not bad. Um, Once again, I'll take a little snippet of this and put it in the notes. And by the way, that seems pretty reasonable, by the way. It's always good to kind of think about, does this answer make sense? Because I'll show you real quick what happens if you don't use the parentheses. You'll see that the answer might not seem realistic. Okay, so this investment, the value when I go to cash it out is going to be $5,102.69. Okay, so back in my calculator, let's just say I accidentally forgot to put the parentheses. So I'm going to go ahead and delete and delete. And so what's going to happen here is that we'll raise it to the power of 12, but then multiply that result by 5. And so my answer is going to be pretty big. It probably will be around 20-something thousand. So let's see, 21,833. And so if you could get a return like that on a 5-year investment, that would be pretty crazy. That would be really, really good. And so some red flags should come up if something were like that to happen. Typically, on most investments, I mean, it can vary, but most investments should double within 7 to 12 years. So whatever money you invest, if your interest rate's going to be somewhere between 4 to 8%, something like that, that's pretty typical. Your investment should double about every 7 to 12 years. And so, anyway, so if it quadruples within a 5-year span, some red flags should go up. Okay, so for the next one, the only difference we're going to do here is we're going to compound quarterly instead. So quarterly, there's 4 quarters and a dollar, just like that. There's going to be 4 quarters in a year. We break it into 3 months is a quarter. So we get 4 of those quarters, and so 4 times a year, you're going to compound it, which means we're going to take that money that you've earned and it becomes part of your investment. And so this one should actually pay out a little less because the previous one was compounding more often. We were doing it every month. This one will do it every 3 months. So let's see, 1 plus 0.039 divided by 4 this time, and then raised to the power of 4 times 5. All right, so let me pull up my calculator. Now, if you have a graphing calculator, what's kind of nice is if you press second and enter, it'll pop up what I just typed in from the previous question. Now I'm gonna have to go up here and change some things. I need to change that 12 to a 4, so I'm gonna do that, and I'm actually gonna have to delete one of my spaces. So I'll press delete. So right there, so 4,200 times 1 plus 0.039 divided by 4, and then raised to the power of, I do need to put that parentheses because if I don't, it won't read it correctly. So 4 times 5, and then close it. And just kind of double check everything. It looks good to me. I think I'm ready to press enter. And here we go. So like I said, it didn't make a big difference. It was a couple dollars. But if we're talking about more money being invested and we're talking about a longer period of time, then it could actually turn into hundreds or maybe even thousands of dollars eventually. And so the more you compound, the better off you're going to be when you invest. Okay, so let's put this answer here. So about $5,099.40. Be careful, that's going to round to 49 cents, okay? So on there, I had to round that 8 up to a 9 because you look at the digit after it. And if it's 5 or greater, you round up. If it would have been a 4, a 3, or a 2, or a 1, or a 0, you don't round up. So in the previous one, I did not round up because it was a 2, right? So I did not round up. So just be careful with your rounding. You'd hate to get that wrong because of a rounding error. Okay, the last formula we're going to look at is going to be if you wanted to compound continuously. So basically, anytime a profit is made, it becomes part of your investment. So what if you wanted your investment to compound trillions of times per second? Remember that special number e that we were dealing with as our base, right, when we were graphing our exponential functions. We have a formula for computing continuous compounding interest that uses e, and it's right here. And this one's actually one of the easier formulas to work with. So it's a equals p e raised to r times t. A lot of times people call it PERT, P-E-R-T, PERT. And so we still have r is going to be our rate, and we have t, it's time in years, okay? And so we're going to use e as the base right there. So let's look at this one right here. So you deposit $5,000 in an account. So that's going to be your principal. And the account's going to earn 7%, which that's pretty good. 7% is a good return rate. And it's going to compound continuously. So that's going to clue you in that you're going to use that formula right there. How much will you have in your account in 12 years? Use the formula and round to the nearest cent. So it should at least double. It'll probably do better than double. But let's go ahead and find out. So I'm going to have A equals my principal, which was 5,000, and then times E. Okay, so times E, and then raised to r times t. Well, my rate, remember, I got to move that to 0.07. I got to move it 2 decimal places to the left. So it's going to be 0.07 and then times t, which in this case was 12. And it's very important that I put that parentheses there for my exponent right there. So let's go ahead and grab our calculator and see what we get here. So I'm going to clear all that out. So 5,000. And so depending on the calculator you're using, if you're using a scientific, they should have the E button there. And they might even have, if you look right here, I've got e to the power of x right here. It's kind of next to my number 4. It's written in yellow. So if I press the yellow button first, and then press this LN button right here, which you're going to learn about actually in the next section, 4.2. Anyways, so second, I have to press second and then ln. It'll give me e to the power of. So it already does that for me. It gets it ready. I'm ready to plug in the power. The other option would be if you look over here by my division button, I also still have to press the yellow button first and it will give me e. But it won't give me to the power of. So then I'd have to type that and then I'd have to open up a parentheses. So it's probably better if you use the other button, because what I like about it is it automatically opens that parentheses for you, like e to the power of parentheses. So let's see, 0.07 and then times 12 and then close it. And I'm ready to go. And so, yep, it's worth a little $11,581. So more than doubled, which is good. Like I said, ideally you want that your investment to double every 7 to 12 years. Typically, the average, I would say, is probably about 10 years, especially if you're investing in something kind of safe, which is not a bad thing. And so, if you think about it, millionaires, if they just invest some of their money every 10 years or so, they're going to double it. And so that's why the rich get richer, right? So, it's always kind of smart to start investing early if you can. All right, so here we are. So we're going to have 11,581 point, and now this is going to round to 0.83 right there. So we don't want to round that 3 up. We're going to keep it there. And there we are. Okay, so that kind of covers part of the application you're going to see with these exponential functions. And so as we move forward, the last section we'll do a couple more word problems with this, but moving forward it's going to kind of be more the application. And we're going to learn about the inverse function of exponential functions. And so if you have any questions or concerns, just let me know.